Some distant galaxies appear older than the universe itself today. This is not a cosmic paradox, it's a measurement puzzle. Picture a tiny red smudge in a deep Hubble field, dim and ancient-looking. Astronomers estimate ages by reading a galaxy's light spectrum to infer how long its stars have been shining. If these estimates were wrong, our cosmic timeline would need serious revision. Spectra carry fingerprints of stars, dust, and elements, which we fit with models to infer age. A red spectrum can mean old stars, or dusty young stars masquerading as old. So the headline claim often collapses under closer scrutiny. Astronomers treat a galaxy like a layered archaeological site. Light arrives carrying a fingerprint of the galaxy's stars and gas. Spectroscopy splits that light across wavelengths, revealing chemical lines and continuum shapes. Those lines set the clock for cosmic history, so accuracy matters a great deal. Absorption lines show which elements are present, and their strengths hint at age. Model spectra assume star formation histories, then fit the observed light to derive ages. A red spectrum often suggests old, low-mass stars dominate the glow, but identical redness can come from dust reddening instead, so spectroscopy is powerful, yet ambiguous without extra constraints. Stars carry chemical fingerprints that subtly tint their light. Metallicity is the fraction of elements heavier than helium in stars. Metal-rich populations can masquerade as ancient ones, so interpretation matters. Metals change stellar atmospheres, altering emitted colors and absorption lines we observe. Fitting routines can trade higher metallicity for older age and still match the same spectrum. This degeneracy survives across visible and near-infrared wavelengths, and it confuses simple fits. For example, a 3 billion-year metal-rich population can mimic 10 billion years in color. Thus, composition uncertainties can push age estimates far older. Dust grains lurk between stars, scattering blue light preferentially. Dust extinction reddens the spectrum, like a cosmic filter on starlight. If uncorrected, dust makes young galaxies appear deceptively old. Absorption removes blue photons, while scattering redirects others across wavelengths. Different galaxies follow distinct extinction laws, so corrections are not universal. A dusty starburst at Redshift 8 can mimic an old, passive galaxy in visible light. Infrared observations reveal dust emission and break that degeneracy across wavelengths. So measuring dust is essential before trusting age claims. Redshift tells us how much the universe stretched since emission. Cosmology translates that redshift into a look-back time we can interpret. A small parameter shift changes inferred galaxy formation times significantly. Hubble's constant sets the expansion rate, and it affects those time conversions directly. Matter and dark energy densities also shift the redshift age mapping in subtle ways. Tension in Hubble's constant illustrates how cosmology uncertainties let ages drift. Changing H0 by a few percent moves formation times measurably. That shift can be hundreds of millions of years, altering formation timelines. So cosmology uncertainties must join age discussions always. Telescopes collect photons, and detectors record them imperfectly. Instrumental effects bias spectra, and thus age fits if uncorrected. Even tiny calibration errors change fitted ages by significant amounts. Background subtraction, detector sensitivity, and flat fielding introduce offsets in spectra. Low signal-to-noise data pushes fits toward simple, and sometimes wrong, solutions. A noisy spectrum may favor an old, passive template incorrectly. Careful calibration and repeated observations lower that risk dramatically. So rigorous instrument control is essential for reliable cosmic ages. Massive foreground objects bend and magnify background galaxy light. Gravitational lensing can boost faint galaxies into view easily, but lensing can blend multiple regions, confusing age signals in a single spectrum. Different star-forming knots map to different image positions and then overlap in projection. The combined light spectrum looks like a single, mixed stellar population to observers. A lensed arc might mix a dusty knot with a blue, young knot in one spectrum. High-resolution imaging and forward lens models separate those components cleanly. So lensing aids discovery, but demands careful deblending of spectra. Stellar models predict how a star's light changes with age across wavelengths. Population synthesis combines many stars to predict integrated galaxy colors. Uncertain evolutionary stages skew those predicted colors and the ages we infer. Phases like the thermally pulsing AGB emit strongly in the infrared, and they affect fits dramatically. Assumptions about binary stars, rotation, and mass loss also change predicted colors. Including a stronger AGB phase can lower inferred ages by 1 billion years. Model differences like these explain large shifts in published age estimates. So model choices must be transparent and tested carefully against data. Some high redshift galaxies tell clearer, multi-wavelength evolutionary stories. Maxone 1000, 149 JDUN offered oxygen emission that dated early star formation remarkably early. That evidence shows stars formed very quickly after the Big Bang in certain regions. Emission lines trace ionized gas, and they timestamp starbursts precisely. Combining emission line data with continuum fits constrains stellar ages tightly. Analyses place star formation at roughly 500 million years after the Big Bang. That number fits comfortably below the universe's accepted age today. So careful, multi-wavelength work resolves apparent age contradictions cleanly. The apparent older-than-universe galaxies do not break cosmology. They highlight measurement limits and the assumptions we make when interpreting spectra. Getting ages right matters for every chapter of cosmic history. The solution combines broader wavelength coverage and better physical models of stars and dust. High-resolution imaging and submillimeter dust maps separate confounding factors cleanly. Improved stellar physics reduces model-driven shifts in age estimates across samples. JWST plus ALMA already narrow uncertainties dramatically for several objects. So the paradox dissolves as data and physics improve. Remember the initial takeaway: this is a measurement puzzle, not a paradox. If you liked this deep dive, subscribe for more friendly Cosmic Explains.